right. Sorry for the delay getting started this morning. For some reason, all of the online systems decided to sign me out of absolutely everything. So I had to take care of that before we actually could do anything this morning. Sometimes I wish I just came in and just wrote on the chalkboard with notes the entire time so I didn't have to set all this stuff up every morning. This is the last day we're going to be talking about new stuff. Okay, so Monday is going to be wrapping up the course, reminding everybody about what we learned this term, talking a little bit about what to expect on the exam, but I'll also talk on Monday a little bit about what to expect after third year civil engineering in general, right? So you don't get a lot of insights into what to expect after third year or even after graduation, so I'll provide a little bit of context for what this course can do for you in your future, both in the next year of the program and after that. Just a quick reminder about the student opinion survey. I'm sure everyone here has filled it out, but if you're watching the video right now, you should use the phone to scan the QR code and go fill out the student opinion survey. Last I checked, we were almost halfway through the class, which is great. I usually like to get at least 50% of the class participating. That way I'm relatively sure that the cross-section of responses is reflective of the general course. So in the last few days of the class, we've been talking about combined loading. The first day we talked about combined tension and bending, and we introduced the form of the interaction equation that we're using for checking members under combined loading. Last day we started looking at combined compression and bending. For tension and bending we had two limit states, strength and stability, or lateral torsional buckling. For combined compression and bending, or for beam columns, we've got three limit states. We have strength, which is yielding of the compression flange. We've got overall member strength, which is flexural buckling that's made worse by the presence of bending moment. And we've got lateral torsional buckling that's made worse by the presence of the axial load in addition to the bending moment. We've also looked at these U1 values and where they've come from and what they're intended to represent in the combined loading scenarios for combined compression and bending. Today we're going to look a little bit at this expression and we're also going to look at the plastic interaction that we looked at for combined tension and bending in the context of beam columns. Okay, so today we're focusing on beam column section class. We already know how to classify beams, right? Class 1, 2, 3, or 4. Changes a little bit when we've got that compression force there. Doesn't change at all when we have a tension force. So for combined tension and bending, you classify the member the same way you would if there was no tension force at all. Beam columns, that's not the case, and so we're going to look at how we classify sections. And then once we figure out how to classify sections, we'll be able to determine, are we going to check linear strength interaction that we talked about the other day, or do we have to check plastic strength interaction, which we're going to talk about today. So a reminder of what we talked about in tension and bending when it came to plastic strength interaction. We looked at, for class 1 and 2 sections, when we can develop the plastic stress distribution, what the interaction between the maximum permissible tension and moment might be on that section. And for strong axis bending, there was a nonlinear interaction that we linearized with the red line and the black line. And for weak axis bending, there is a very nonlinear interaction that we linearized with the blue line and the black line. Okay, so the beam column or the plastic strength interaction diagrams are basically a piecewise linear function where we've got the combined compression and bending as well as the bending only limit state that we need to check. And we also introduced the idea of the U1 term and what it's intending to account for in terms of the amplification of bending moment present on our beam column due to the fact that we have displacements caused by the applied bending moment and an additional moment at midspan that's equal to the applied bending moment plus the CF delta term, and we call that entire midspan moment this U1x MFX. So today we're going to look at how to put all these things together in the context of beam columns. After today, you should be able to determine the section class for members with combined compression and bending, or for beam columns. Apply the plastic strength interaction equations to check the strength of a member with combined compression and bending, and describe how to design, roughly speaking, members with combined compression and bending. Spoiler alert for that one, there's no table that really helps us design beam columns. What you have to do when you're designing beam columns is you just need to pick something and then keep changing it until it works. There's so many things going on here. It's a compression member, it's a bending member, the section class changes depending on the load. And so really you need a program like StatPro or an Excel spreadsheet to figure out what section is going to be best in this case. Does anyone have any questions about these three final learning objectives before we get into the content for the morning? Okay, so we need to unpack section class for beam columns. And you've already seen the expression, but I want to talk a little bit about what the expression implies in terms of how the section class changes with the applied loads, and what it's intending to do in terms of treating it as either a pure beam or a pure column and something in between when we've got combined loading. When we looked at columns in pure compression, we wanted to make sure that we weren't going to get local buckling of the web or local buckling of the flange before we reached the yield stress, right? And if we did that, we didn't have to reduce the area, and we could use the phi Fy divided by all the junk in the denominator to calculate the compressive resistance. In order for us to not have to reduce the area, the width to thickness ratio, where this was BEL, which was half the flange width, divided by T, which is the flange thickness, that had to be less than or equal to 200 divided by the square root of Fy. And that comes from the presence of a uniform compressive stress in the flange. Okay, that uniform compressive stress can cause local buckling, and as long as we have a uniform compressive stress, we just have to make sure the width to thickness ratio meets this limit for the flange. For webs, BEL was H, which was the clear distance between the flanges, which is D minus 2T, and T is equal to W for the web check. As long as BEL, which is D minus 2T, divided by T, which is W, for the web was less than or equal to 670 over the square root of Fy, we were confident that we can develop the yield strength in the web when we apply a uniform compressive stress on the cross-section. Okay, so that's stuff we've already talked about. For beams, the only thing that changed was the width to thickness ratio limit for the web. Okay, this is to consider the beam as a class 3 section. Okay, so for columns, you just try to get the yield stress everywhere in the cross-section. For class 3 sections, what we're trying to do is at least develop the yield strength in the extreme fiber of the flange. Because the stress is still relatively uniform throughout the flange, that width to thickness ratio limit doesn't change, right? It's a uniform compressive stress in the flange. I mean, it varies very slightly from the bottom of the flange to the top, but we could assume that the average stress is about Fy in the flange. It's uniform, and so the same limit applies. When we looked at webs for pure bending, when we were trying to get a class 3 section, what we're trying to develop is a linear stress distribution of compressive stresses in the web. And if we compare that to the uniform compressive stress over the web for pure compression, we saw here that half the web was under compression, and there was significantly less stress overall, right? Half of the stress effectively, because it goes from 0 to almost Fy here. And so because there's less stress over less of the web, we have a less strict width to thickness ratio in order to develop that kind of stress distribution. Okay, so that's stuff that we've already talked about. When we're dealing with beam columns and we're adding a compression force, as we saw previously, as long as we're in the linear elastic range, we can assume that we can add these stresses together, the resultant stress from compression and bending. And as we add compression, the neutral axis shifts from the center of the section down towards the flange that's in tension. So as we add compression, more of the web experiences more compression. And so we're reducing the limit based on the applied compression force. And basically what we're doing here is if CF is 0, then this whole expression just turns into 0 when we get 1. And we're just left with the expression that we had for pure beams before. But as CF approaches the yield resistance, phi Cy, that's basically equal to phi A Fy. As CF becomes close to Cy, that means we apply less and less bending moment before we get to the strength. And we're approaching the case of having pure compression. Okay, so as we approach pure compression acting on the section, this becomes 1 instead. This whole term here becomes 0.35, and 1900 times 0.35 is equal to 665, which is very close to 670. Okay, so what we're doing when we're trying to determine the section class for beam columns is we're somewhere between pure compression and pure bending, and the intent of the expression here to determine whether or not, for example, we have a class 3 beam column is basically linear interpolation between pure column and pure bending. Okay, so that's what we're trying to accomplish here. What that means is section class can change with load, which is kind of annoying, right? You might have one combination of CF and MF where you have a class 2 beam column. For a different load combination, you might have CF and MF where you have a class 3 beam column. And so you have to check the interaction equation differently depending on the section class that you get from those calculations. Are there any questions about that concept of interpolation between pure bending and pure compression, or why we may result in having a different section class with the different compression forces that we could apply? Are there any questions about those concepts before we continue? Okay, so that's for class 3 sections. We've got a bunch of other things to check. So the flange does not change. We use the same width to thickness ratio limits that we did for pure flexure. 200 for class 3, 170 for class 2, 145 for class 1. But now, when we're dealing with elements supported along two edges, like webs of bisections, that are subjected to combined axial compression and bending, then we're dealing with 1100 times some stuff, 1 minus some stuff times CF over phi CY, 1700 with a 0.61, and 1900 with a 0.65. And basically, the same trend happens as we try to improve the section class from 3 to 2 to 1. The limit on the width to thickness ratio is going to get smaller and smaller, meaning we need to have thicker and thicker components. In this class, we're focusing on strong axis bending and compression. You could have weak axis bending and compression as well, in which case there's a separate set of things that you need to check. We're not going to get into weak axis bending and compression in this class, but you'll notice that for class 3 sections, it's very similar. For class 2 sections, it's completely different. And for class 1 sections, it's completely different. Okay, so it depends on what CF is in terms of the yield compression force that you can develop in the column, and that's as much detail as we're going to get into on that. So I'm going to focus on this for a minute because this is what we're going to be focusing on in this class. So beam columns, why is that doing that? That's annoying. There we go. I'm just going to delete that to stop it. Okay, I'm not going to delete that anymore. So we're dealing with these 3 potential limits for class 1, 2, and 3. And if we already know what steel we're working with, we've got square root of Fy down here. And if we know what section we're trying to classify, we also know what Cy could be. Cy is just the yield compression force. I don't know why they write it this way. They should just write it as AFY. Cy here is AFY. And so if we know what section we're dealing with, we know what the area is. So the only thing that changes or has the potential to change for a given cross-section basically is the factored compression force. So H over W is constant for a section. Everything else is constant except for CF. There's a very neat table in the handbook, table 4.7, that helps us. It's the only table that's helpful for beam columns in the handbook. It tells us how we can quickly classify different webs of different sections based on the CF to CY ratio. Okay, so a bigger CF to CY ratio means that the limit gets smaller. Basically, if we have a CF to phi CY ratio for, let's say, W690 by 192, the higher the compression force is, the higher the CF to CY ratio, and the worse the section class is going to be. All you need to do is, for the section, figure out what phi CY is. That's just AFY multiplied by the resistance factor. You take CF and divide it by that value. And as long as the ratio you get is less than this value, that's class 3. If it's less than this value, it's class 2. If it's less than this value, it's class 1. The other thing that's nice about the table is it tells you what the class of the flange is. Okay, so over here, you already know that the class of the flanges in this case is 1. And so you just need to figure out then, is my section going to be class 3, 2, or 1 based on the CF to CY ratio. You're going to see a bunch of things here where you just have 1. What does it mean for example, about, let's just say W610 by 241, there are no ratios here, and we have 1 in this column. What does that imply, do you think, about that section? Well, it basically means it can never be class 2 or 3. It's always going to be class 1, right? So CF over phi CY, right, as long as you're designing it properly. If you exceed phi CY anyway, your column's going to fail. So that should always be less than or equal to 1 anyway. And so all these sections that have strikeouts or M dashes in the 2 and 3 column and a ratio of 1 in the class 1 column, these are always going to be class 1 sections regardless of what the axial load is. Okay, so some sections will change class depending on what the axial force is. Some sections will not change class and will always be class 1. Okay, so we talked a little bit about section class, equations that you can use to determine limits on the width to thickness ratios when you have combined compression and bending. And there's a table here that helps make that check a little bit quicker because it gives you the section class for the flange, and you just calculate CF over phi CY to figure out the section class for the web. I hope to see that in an example today, but are there any questions about that table or the section class checks before we continue? Okay. So let's say we got a class 3 section. Well, you go and do the stuff that we talked about on Wednesday. If you get a class 1 or 2 section, you go ahead and do the stuff that we're going to talk about now. And so clause 13.8.2 of CSAS 16 tells us how to check the strength of class 1 and 2 sections, specifically of I-shaped members. Okay, in this class we're just going to be dealing with wide flange sections as beam columns. It's a little bit different for HSS, and I think those, well, it has to be doubly symmetric to be considered class 1 and sometimes class 2 anyway. So we're going to focus on wide flange shapes, and therefore we're going to look at 13.8.2 for that reason. When we think about the nonlinear interaction, well, it doesn't change. All of a sudden, we're just flipping tension to compression. And so in terms of cross-sectional stresses, we're just doing the same thing. We're trying to prevent the yielding of the cross-section, and we're trying to check overall member strength. So in terms of the nonlinear interaction effects that we talked about for combined tension and bending, it's the same for combined compression and bending. Okay, the only difference is now we sort of have this amplification factor from the P delta effects that we didn't have there from the applied tension and bending. Basically what this means is that when we start to check the cross-sectional strength interaction, we have basically the same thing that we had before for tension, except now we've got the U1x and U1y parameters in there. So the only thing that really changes is for combined tension and bending. This was always 0.6, at least for cross-sectional strength checks, but it's going to change as we go through different limit states. So for cross-sectional strength, just like tension, it's going to be 0.6, and that's an easy calculation. For other things, it might be slightly different. I'll talk about that in a minute. Otherwise, all of the things that we talked about the other day hold true, except we replace S with Z wherever we're calculating moment resistance. Okay, so just like last day, compressive resistance was calculated with lambda is equal to 0, which is phi A Fy. And because we're already calculating phi Cy for section class, it's the same thing, right? That's phi Cy. Moment resistance is phi Zx Fy for strong axis, phi Zy Fy for weak axis, and nothing changes about the U1x calculations. The only thing that changes is as we go to different limit states that we're checking, beta will change for weak axis bending. We calculate it as 0.6 plus 0.4 times lambda y. Can anyone tell me what lambda y is? We've already talked about lambda before. That had to deal with compression members. Lambda y might imply, you calculate lambda for what? Well, y, subscript y, always implies, unless it's yield, a property about the weak axis, right? So lambda y is equal to the square root of Fy over Fey. So you calculate the critical elastic buckling stress for the weak axis, use that to calculate lambda based on the weak axis, and then beta is going to change from 0.6 to 0.6 plus 0.4 lambda y, but it doesn't have to be taken as anything bigger than 0.85. Okay, and the reason for this is it's too unconservative to use a value of 0.6, as stability effects and flexural buckling limit states tend to govern the behavior of the beam column. Otherwise, again, we're just replacing S with Z here in the moment resistance calculations, and U1X and U1Y are calculated the same as we talked about last day. The last thing is lateral torsional buckling, and nothing really changes. We've got the same calculation for beta, 0.6 plus 0.4 lambda y. Minimum resistance for compression for CR, 13.6 for MRX, except now we're doing everything based on MP instead of MY for those checks. Weak axis moment phi ZFY, U1X and U1Y, all the same stuff. Okay, so the only thing that's really new today is, do we have a class 3 or a class 1 and 2 beam column? We talked about how to classify beam columns based on the web primarily, as well as the flange. And then from the interaction equation the other day, we get 0.85 and beta just changes from time to time between the limit states. Okay, so there's nothing groundbreaking today that we need to talk about. The only thing that's really important now, though, is the bending only check. The bending only check was important the other day because you can sort of fudge S16 if you just check this limit state here. If we have a class 3 beam column, 0.85 is 1 and beta was 1. And so we could reduce MFX and MFY by the U1X and U1Y values if omega 1 was less than 1, and we're not allowed to do that. But bending only for class 2 beam columns is absolutely critical because we don't want to exceed the strength, right? This is the equation of the interaction diagram. So that's the CF over CR plus 0.6 MY over MRY. And so we can't go out beyond the bending only strength. And so this check is crucial for the overall member strength of beam columns. Okay. Does anyone have any questions about how this is different and similar to class 1 or 2 sections under combined tension and bending, and how it's similar and different from the interactions of class 3 beam columns? Are there any questions about these concepts before we continue? Okay, so that's great. We've got lots of time for an example, which is what I was hoping for. We're going to go back to the same example that we started looking at the other day. So just for context again, this column is a wall column. The wall is going in and out of the page here. This is just a roof beam at the top that's supporting the beam column, and wind is blowing on the face of the building this way, and the result is that from the cladding on the members between columns, we get the point loads of 30 kilonewtons acting on the beam column. And the other effect is that we're going to assume, I don't know if it's reasonable or not, but for the purposes of this example, we're going to assume that the members that are carrying the cladding will also provide lateral support to the beam column at those 3 intermittent points. Okay, so we'll assume that it's adequately braced laterally, and we'll also say torsionally at those 3 points. Okay, so we've got an 8-meter tall column. It's the same section as the other day, same grade as the other day, loaded with the same forces as the other day. What we're going to do is determine the section class of the beam column and check the appropriate interaction equations for one of the load combinations that we checked the other day. So we calculated the effects from 1.25 dead plus 1.4 W plus 0.5 snow. There's also 1.25 dead plus 1.5 S plus 0.4 W. We need to check both, but we're not going to have time to do both today. But I continue the checks in the example notes posted to D12. Okay. Are there any questions about what we're attempting to do here before we get into the calculations? Okay. So the first thing we need to do is determine section class, right? So we have, for this load combination of the 1.25 dead plus 1.4 W plus 0.5 snow from the example the other day, CF is equal to 900 kilonewtons. MFX was equal to 168 kilonewtons. And just that we have it here, U1x for this load combination was equal to 1.20. There's no weak axis bending present on this column because, well, there's no loading applying any kind of weak axis bending. We've got an axial force and loads bending the column about the strong axis. Okay, so MFY is 0 in this case, and we're not going to consider the weak axis bending effects because there's none to consider. Okay, does anyone have a handbook with them? I was sure. Katie's got it here. Thank you. Closest one. So I was very determined to remember to bring it today, and of course I didn't. But what we're going to do is we're going to go to the tables here. And so what we need to check, if we recall, is we're checking the flange to see if it's class 1, 2, or 3. And we're going to check the web to see if it's class 1, 2, or 3. But now the web check depends on the applied axial force relative to the yield load for that particular member. So, does anyone have any ideas where you could very quickly find some information in the handbook about any of these quantities? We need to calculate phi cy. What's the fastest way to get phi cy used in the handbook? We could go find the area of a W310 by 64 and multiply that by Fy, and then multiply that by Cy. Does anyone know of anything faster? So I guess I'm saying 360. What do I have written there for the example? It should be that should be 360, I think. 360 by 64. Sorry. So if you go to the handbook, what the hell's going on here? There it is. So if you go to the handbook and you go to the column selection tables, this is something that you should remember if you were ever dealing with a beam column on an exam and you were trying to do things quickly and I didn't tell you otherwise. In addition to the compressive resistance for all of the unbraced lengths, I guess this is camera time. So in addition to the compressive resistances for all these effective lengths, one of the values that it gives you is the compressive resistance for a length of 0. Is that useful to us today? What does the compressive resistance for an effective length of 0 represent? It's the yield load, right? Phi Fy, because when KL is 0, then lambda is going to be 0. We can't buckle a column with a effective length of 0. And so that means if we want phi Cy, we can just come to the column selection tables and find the resistance for KL0. Okay, so phi Cy, when I'm calculating that, is 2,430. All right? So phi Cy is 2,430 kilonewtons. That comes from the column selection tables. Right, and so just for reference, that's on page 4-21. Okay, so quickest way to find phi Cy is to look it up in the handbook. So to use the tables for section class, we need CF over phi Cy. That's equal to 900 in this load case, divided by 2,430 kilonewtons. Do I have that ratio here? I'm sure I do. That's equal to 0.37. So all I need to do is go to table 4-7 in the handbook, and I'll show you where that is here. So in the handbook, we're at table 4-7. Starts on page 4-100. It's only on these 2 pages. And what we need to do is find our section. Okay, so we need to, actually maybe it's over a couple pages. There it is. So we need to find our W360 by 64. The table tells us the flange is class 1, and it tells us the ratio of CF to phi Cy has to be less than 0.913 to be class 3, 0.895 to be class 2, 0.765 to be class 1. We have a ratio of 0.37. What does that mean about our web? It's class 1. Excellent. So table 4-7 tells us, web is class 1. It also says flange is class 1. That's from table 4-7. That means that our section is class 1. Okay? So section classification, go to table 4-7. It'll tell you directly what the flange class is. That never changes with load. We find phi cy in the handbook, divide CF by phi cy, get the ratio, use that ratio to classify the web. Done. Okay? So if you're ever dealing with a beam column, unless I say by calculation and checking with accordance with table 2 of S16, classify the section, if I just say classify the section, you should probably do it the fast and easy way. Okay? Are there any questions about what we just did there to classify the section? Okay. So, well, what does that mean? Well, we're talking about plastic strength interaction today. That means we're going to be looking at plastic strength interaction. So we've got a class 1 I-shaped member. So we're going to be going to clause 13.8.2 to calculate the resistance or the interaction ratio for our beam column. Okay? So we've got to check a bunch of stuff. The first thing we need to check is cross-sectional strength. To check cross-sectional strength, we need all these values. However, we don't have any MFY, right? So we don't need beta, we don't need MRY, and we don't need U1Y. There is no interaction effect from weak axis moment because there is none applied. We only have strong axis bending here. So what that means is we need CR, which for overall cross-sectional strength is phi cy. That's convenient because we just looked that up in the handbook. We need MRX, which is phi ZFY, but we can also find that in the handbook, right? So if we go to overall member strength, we're going to be looking at CR is phi cy. We already looked that up in the handbook. That's the CR for KL is equal to 0. That's equal to 2,430 kilonewtons. MRX is equal to phi ZX Fy. We can look up Z, multiply by 0.9 and Fy, or is there a tool in the handbook that we can use to get MRX quicker than that? There are the beam selection tables, right? Well, you know it's a class 1 section. We're looking at the full moment resistance. It's the fully braced moment resistance. And so what we want to do is look at the column with MR in bold, right? We want to be looking here. We're looking for the fully braced moment resistance. And we want to come down and we want to find the section that we're dealing with. Okay, so we're looking for 360 by 64. There it is. And if we look at moment resistance, there it is, right? 354, that's the fully braced moment resistance. That's MR calculated in accordance with clause 13.5, and that's what we're going to be using in our interaction calculations. Okay, come on PowerPoint, get back up here. I know you can do it. 345 kilonewton meters. So we've got CR, MR, and we also have U1X. If we come back to overall member strength check, for us currently, that's 0. We just need CR, U1, MR, and we've already got CF and MFX for the load combination we're looking at, so we can calculate the interaction ratio for cross-sectional strength. Okay, CF over CR plus U1X, 0.85. 0.85 U1X MFX over MRX has to be less than or equal to 1. We have CF, which is 900 kilonewtons, over CR, which is 2,430 kilonewtons, plus 0.85 times 1.20 times 168 kilonewton meters divided by 345 kilonewton meters. If we do that calculation, we should get an interaction ratio of 0.854, which is indeed less than 1. Okay? So, overall member strength, we're just dealing with preventing excessive yielding of the cross-section. For that reason, we use phi CY handbook. We also use phi ZFY, which is phi MP. Handbook 345. We calculated U1X the other day. Mash everything together, we get a ratio of 0.854. Is that acceptable for our beam column? Is our beam column strong enough to prevent failure by overall member strength? Yeah, it's less than 1, right? So we're good. Are there any questions about the calculation of the interaction ratio for overall member strength before we continue? Okay. Sorry, cross-sectional strength. Yeah, again, I hate the term overall member strength. Cross-sectional strength is what we just checked. Thanks, Katie. So next, we need to look at overall member strength. And we were kind of annoyed that beta is going to change, but we don't care what beta is because we have no weak axis bending anyway. MRX is the same. UNX is the same. CR is calculated a little bit differently. CR now is based on, for us, because we only have strong axis bending, it's based on the strong axis flexural buckling resistance. Okay, so we need to calculate CR based on the overall member strength. We need to calculate CR based on strong axis flexural buckling. Did I write cross-sectional strength for that one? Okay, so for overall member strength, CR is CRX. That means we need to calculate FEX. Pi squared E over K XLX over RX squared. So we need Rx for this particular section, and we also need to observe our boundary conditions, right? So we're already bending this column about the strong axis. There's nothing bracing it from the top to the bottom against strong axis deflection or flexural buckling. The column is already bending this way, which means the column under excessive compressive load is going to buckle out like this. K we'll just take as 1 because it's connected to a beam with just a simple connection at the top and a foundation at the bottom. We could use 0.96 like we talked about in lecture 25, but we're just going to keep it simple and use K as 1. And our overall length of that column in flexural buckling is 8,000. So the only other thing we need to do is look up Rx. I will, I guess, turn the camera on just in case no one's looked up Rx for a section before. So we need to go, and we can look in a couple different places. We could look at the sectional properties, or we can also look at the compressive resistance tables. Let's just go back to the compressive resistance tables because we already looked at those before. So we're looking at our W360 by 64. If we come down to the bottom, it tells us here Rx and Ry. So for our calculations here, Rx is going to be 148. We could also try to use the Rx over Ry ratio to get a compressive resistance from here. It's not going to be exact, and so we might as well just go through the calculation instead. That gives us pi squared times 200 times 10 to the 3 MPa divided by 1.0 times 8,000 millimeters over 148 millimeters squared, and we get an FEX value of 676 MPa. Okay, because we have strong axis bending for overall member strength CR CRX, that means we need to calculate FEX. We're using K as 1, L is 8,000, and we use R for the cross section about the strong axis. Are there any questions about that calculation before we continue? Okay, so lambda, we might call it lambda x, is equal to the square root of Fy over Fex, square root of 345 MPa. Remember, ASTM A992 grade 50, all W sections all the time, divided by 676 MPa. We get a lambda value of 0.6 Now we can calculate CRX. CRX is phi A Fy divided by 1 plus lambda to the 2n all to the 1 over n. Now, we're not using a reduced area because our section class is 1. We'd only be using a reduced area if we had a section class that was class 4, or if the web exceeded the 670 over the square root of Fy for that particular case. We're dealing with a class 1 section, so we'll just calculate phi A Fy based on a non-reduced section resistance. Phi A Fy is also Cy, so I can also make my life easier here. And instead of finding the area, I'm just going to write this as phi Cy, which is 2,430 kilonewtons. We already looked that up in the handbook. Divided by 1 plus lambda, which is 0.715 to the 2n, all to the 1 over n. What value of n do we use for hot rolled sections? 1.34, 2.24, 1.24, 1.34, 2.24. 1.34 it is, and that's the right answer. Divided by 1.34. We end up with a compressive resistance about the strong axis then of 1,957 kilonewtons. Okay? So, calculate CR based on phi A Fy. Shorthand, we already found phi Cy, which is the same. Cy is just AFY. So we just plug that straight in for phi AFY. Divide through by the junk in the denominator, get a compressive resistance of 1957. Are there any questions about that calculation before we continue on? Okay. So now we have everything we need. We've got MRX, which doesn't change, and we've got CR calculated in accordance with the standard here. So we've got CF over CR plus 0.85 U1x MFX over MRX. That's equal to 900 kilonewtons divided by 1957 kilonewtons plus 0.85 times 1.20 times 168 kilonewton meters divided by 345 kilonewton meters. The ratio calculated this way is 0.944. We're just squeaking by now, about 5.5% less than the limit at 1. Okay, so only thing that changed here was overall member strength. For overall member strength was the compressive resistance. Compressive resistance goes down, interaction ratio goes up. All good? Okay. So the last thing we need to check then is lateral torsional buckling. Or bending only as well, but bending only is not going to be a showstopper here. So lateral torsional buckling, now CR is the minimum compressive resistance, and so it's either CRX or CRY. MRX is now strong axis moment resistance from clause 13.6, which is for unbraced beams. U1x doesn't change, has to be bigger than 1. Our value of U1x is not less than 1, so we're all good here. Okay. So let's look at our problem. Now we're looking at buckling about the weak axis, which is in and out of the page, so I can't really sketch that here. But basically, it's going to buckle between the points of lateral restraint. We'll assume that at these girts, or these members that carry the wind load, we've got adequate restraint to force weak axis buckling with a reduced effective length. Okay, so for lateral torsional buckling, we're going to take KYLY as 2,000 millimeters. And for the lateral torsional buckling calculations, we're also going to take L is equal to 2,000 millimeters. Okay, so the girts are going to brace the compression flange against lateral torsional buckling, unbraced in between those points, and same for weak axis flexural buckling. Okay, so we need, whoa, I guess I was zoomed in there. I don't think I can make those any bigger, so I'll just rewrite that quickly. LTB, KYLY KYLY is 2,000, and L is 2,000. So we need to calculate CR is the minimum of CRX, CRY, CRZ. CRZ is going to be higher than CRY because we're going to assume that KZLZ is equal to KYLY. Torsional buckling is never weaker than weak axis buckling for wide flange sections if the effective lengths are the same. Okay, so we're going to eliminate CRZ. We already calculated CRX to be 1957. Is there a simple way for us to figure out what CRY should be for this value of KL? If you said handbook, you're correct. Right? So we already know that these values of CR are based on the weak axis flexural buckling resistance. For our W360 by 64, we'll come here and we will see for an effective length of 2,000, the weak axis compressive resistance is 2,120. Is that higher or lower than the strong axis compressive resistance that we already calculated? That's higher. So we don't take the weak axis buckling mode. We take CRX, which is, oh, what the hell was that? 1,957. Whoops. Oh no, I didn't mean to close that. Let's try that again. MRX. Is there a quick way for us to figure what MRX should be for an unbraced beam? Handbook, right? That's the easiest thing we can do. Now we have to remember the beam selection tables. The values of unbraced moment resistance are calculated for an omega 1 value of 1. Based on our moment diagram, our omega 1 value is not 1, so our omega 2 is not 1. It's probably 1.13. But let's deal with that later. So we'll flip through, try and find our section. I missed it. So we're going to look at a W360 by 64. There it is. And we're going to come over to the column for 2,000. Oh, look at that. There is no entry here. What does no entry mean? It means that L value, 2,000, 2,500, they're all, oh, I lost myself here, 64. We've got 2,870, 2,000 is less than that, 2,500 is less than that. They're all less than the unbraced length that starts to cause lateral torsional buckling. That means that even though we have an unbraced length of 2,000 millimeters, we still get the fully braced moment resistance back. Okay, so in this case, MRX is still equal to 345 kilonewton meters. Oh shit, I keep writing that wrong. 354 kilonewton meters. So what that means is, well, nothing's changed. We had the exact same values for overall member strength, right? We got CRX, and we had the exact same value for moment resistance, MRX. Despite the fact that we're checking lateral torsional buckling, what this is indicating is our column is sufficiently braced to prevent lateral torsional buckling from governing as a failure mode. Okay? If we do this calculation, we're going to get the exact same interaction ratio because all the values are exactly the same. Okay? So, we have a problem where we've got a column carrying some wind that causes bending, some snow and dead load, some snow and dead load that causes axial force. It's a beam column. We have to classify it. We got class 1 using table 4-7. We already had U1x because we calculated that for this column last lecture. We checked overall member strength with the appropriate values of CR and MR. They were the full yield load for compression, which comes from the handbook. Fully braced moment resistance. Again, I must be dyslexic. All the ratios are right. This is just 354, not 345. And the moment resistance also comes from the handbook. The strength is acceptable. For overall member strength, CR changes. It's based on the strong axis flexural buckling resistance. So we have to calculate FEX and lambda x and use that to get the strong axis compression resistance of something a little bit less than phi cy, 1957. MRX is the same. We get a higher interaction ratio. For lateral torsional buckling, CRX is the minimum compressive resistance. MRX also happens to be forced to be the fully laterally braced moment resistance. That's telling us lateral torsional buckling is not going to be an issue for this particular beam column. Okay. The last thing we check is bending only. Of course, MFX over MRX. That's equal to whatever it was, 168 over 354, which is clearly less than 1. Okay. Are there any questions about that example or what any of these calculations mean before we wrap up lecture for the day? Okay. So that puts some pieces together. I went from 919 to 923 real quick. You should be able to do all these things. You can read them yourself. Unless anybody has any questions, we'll see you all Monday morning.